Hi, everyone. I guess I'll get started since it's time. My name's Patrick. I work at H2O, which is a machine learning software company located in Mountain View, California, right down the road. I'm going to be talking today about a set of practices that I think will be very important as AI becomes more mainstream. And I'm going to try to talk about them in pretty general terms. You'll see on the slide sometimes I do mention specific software, and that's just because I thought it was kind of an Easter egg, something that was kind of unique and interesting to me that I thought maybe other people hadn't heard about. So if you work in a regulatory environment, especially for credit scoring, a lot of what I'm going to talk about will probably sound familiar. If you don't, hopefully, it'll be kind of a learning experience, and a lot of the talk is mapping best practices from model risk management in banking to kind of a broader spectrum of models. That's the basic idea. And if you do work in credit scoring, I hope that I'll show you some kind of newer research techniques that we were thinking about at H2O that you could think about and might not have heard of before. Okay. So very quickly, these are the phases of the sort of workflow that I'm going to go through. And I will try to save time for Q&A, but if not, just follow me out or find me at the H2O booth. I'll be around and happy to answer your questions. Okay, so without any further ado, here's the workflow that I think you wouldn't shoot yourself in the foot with commercially, and would also take into consideration a lot of important human aspects of what we do. And as machine learning models, weak AI-based decision support systems become more and more prevalent in our lives, these kinds of considerations will become more and more important, both for ethical reasons, security reasons, fairness, understanding, explanatory reasons. And then if you don't care about any of that stuff, this is a great way to prevent yourself from losing a ton of money with machine learning. So you can think about it like that also. Now, in my opinion, I think that these concerns are very serious, okay? I genuinely think, and I've talked to a lot of people about this today even, that our failure as a discipline to address the things that you're seeing on the slide on our own could very well result in just potentially draconian over-regulation, okay? And I'm actually very pro-regulation, the right kind of regulation. But I'm very worried that if we don't take care of these things on our own, that government bodies that are perhaps not as educated about what we do will just come in and say, you can't do this, you can't do this, you can't do this, you can't do this, you can't do this. And I don't think anybody in this room wants that. I also just think it's the right thing to do. And I'm not some kind of AI fairness expert, and I don't think I'm the right person to tell a bunch of AI fairness stories, but I certainly think I can advocate for fairness of AI methods, whatever that means. And that's another current that you'll hopefully see running through this talk. I would not let the perfect be the enemy of the good here. It would be very difficult for a small organization or even a large organization to do everything on this slide. I think you will be able to tell which parts of this stick out as being applicable to your own work, and maybe that's a good place to get started, right? Like, don't let the perfect be the enemy of the good. Don't try to boil the ocean. Maybe you don't have to do all of these things when you first get started, but hopefully in the future, these things will become more and more common in our workflows. Okay. So I'm going to assume that you can read the slides, and basically we're just going to work through this workflow. Okay, so the old adage, and people ask me about this a lot, yes, garbage in, garbage out still holds, okay? And you need to understand your data. Now, this slide sort of starts from assuming that we have relatively clean data all in one place, which I know is, we're just talking about the very tip of the iceberg here, okay? And there's all kinds of privacy and security and ethics issues with just the data alone. But just to be clear, because it's a question that I get a lot, these slides really only pertain to the modeling process, not to the ETL processes, which I know a lot of people at this conference are probably more into. And I'll stop right here and say they're incredibly important. That's just not what this talk is about, okay? This talk is about the modeling processes. So once you have your data ready to model, whatever that means to you, you need to know what's in it. And data visualization is a very good way to do that. It's certainly not the only way. I mean, I'm talking about very basic things like looking at univariate densities and scatter plot matrices and just good old-fashioned exploratory data analysis. And there are tools that automate this now. H2O has a tool that actually automates this that we call AutoViz, which would bring to your attention sort of anomalous plots. But if you're just coding this all yourself, that's fine too. And you might find the H2O3 aggregator, which is a piece of completely free open source software. You can use that to make samples of your data that will keep the outliers in. They'll keep the statistically significant outliers in your sample. And that's typically the problem with sampling to do data visualization is you could lose the outliers. So this is a nice little Easter egg that I use a lot to visualize big data sets. It's a very scalable procedure that will make samples that preserve outliers specifically for visualization. OK. You need to start with benchmarks, OK? This is maybe one of the, if you're going to do any of this, you have to start with a benchmark, OK? And what does a benchmark mean? Well, a benchmark might mean something like a linear regression just on, or a single decision tree just on your data before you even start doing any feature engineering, OK? And you want to establish a benchmark not just in terms of accuracy, but also in terms of things like disparate impact, or explainability, or different types of security measures. So one sort of theme here is don't just be so solely focused on accuracy, right? Accuracy is important, but I'd claim it's actually not as important as a lot of people think it is because we tend to measure accuracy on static test data sets and then go apply a model in the real world where a lot of the things that we learned in those static data sets don't really apply anymore. So keep in mind things besides accuracy. So fairness, privacy, security, explainability. These things are crucial both for the human-centered aspect of this and probably also for the commercial success of this model. So you have to know where you started from to know if you're doing better or worse on any of these metrics. Okay? So always establish a benchmark. And that may mean different things to different people. OK. So feature engineering. There's all kinds of ways to do feature engineering. And you should think about what's more important to you. What I'm trying to avoid here is getting into a situation where there are features in my model, such as features extracted from the middle hidden layers of an autoencoder neural network, or some kind of sophisticated PCA or nonlinear PCA that I'll never be able to explain. Okay, that's the main thing that I'm watching out for. But you may be more worried about encryption, right? So maybe you want to encrypt your features. You may be more worried about privacy, which again, encryption would cover. You may be worried about some other aspect. But just keep in mind these features that you put into your model, you're going to have to explain them to people. You're going to have to justify them somehow. And so do not introduce undue complexity into your model process in the feature engineering part of your workflow. And I see that happen a lot, actually. So just remember, if you're using those autoencoder features, you might have to explain them one day. And that's going to be very, very difficult. So think about the kind of features that you're using in your modeling workflow. OK. There are a lot of different things that you can do to your data to make it more private or to make it more fair. And again, I recently saw a presentation called the 21 Definitions of Fairness and Their Politics. So fairness is a very fraught subject. But there are techniques, and I have this nice open source package from IBM, that will help you pre-process your data to remove potential causes of disparate impact. And disparate impact is when your model treats different groups of people more differently than you intend it to. Okay? And I like to talk about disparate impact instead of fairness because disparate impact is legally defined. So the fundamental definition, the easiest definition of disparate impact is when your predictions are more than 20% different for one group versus another group. And so in this IBM open source library, there are tools that would actually help you pre-process causes of disparate impact out of your data. And I think that's an interesting thing to consider. I'm not necessarily advocating that you do that, but I think it's an interesting thing to consider. You can also pre-process for privacy, remove PII, I think personally identifiable information. I think that's a really important part of a modeling process that can get you into big, big trouble down the road is if your model is accidentally exposing people's personally identifiable information. So keep that in mind in your pre-processing steps. Okay. Modeling. We all want to do deep learning, right? I want to do deep learning too. But when we use the most complex types of machine learning models, we again get ourselves into trouble potentially when it comes to explanation or when it comes to proving that my model does not have disparate impact or when it comes to proving that my model hasn't been hacked, okay? Your model can be hacked. It's not a very likely thing to happen, but it is possible. People are starting to publish papers about this. And if your model is so complex that you can't explain it, how will you know if someone has gone in and changed it? You won't know, okay? So keep in mind, I can use these very complex models to sometimes have better accuracy on static test data sets, but what are you giving up when you do that? You may potentially be giving up explainability. You could potentially be giving up security. And what's more is there are newer methods that are nonlinear, very accurate, but also designed to be directly interpretable. And I have some listed on the slide there. And my favorite method for doing interpretable models is monotonic gradient boosting machines. And so gradient boosting machines are a very popular kind of tree-based modeling algorithm. They're very accurate. They're very robust. And you can constrain them to be monotonic. And you can do that in XGBoost, very popular open source package. H2O, you can do that. And when you do this, I think it really helps you on the interpretability side, right? Because when your boss asks, how does the model work? Well, you can say something like, well, it's a little bit complicated, but as the customer's savings account balance goes up, our probability of sending them a coupon only goes up. And I promise you, if you can say something like that, you're going to put a lot of people at ease right away. So monotonicity is a very important aspect of interpretability, and it's something that's just easily and freely available in very popular libraries like XGBoost and H2O. So that's a little trick to keep in mind that I really like. If you're interested in trying kind of more sophisticated, less well-known types of interpretable models, I have some listed on the slide, such as explainable and neural networks, learning fair representations, which is actually a linear model, but it's designed specifically not to weigh people's personal characteristics too heavily. PATE is a type of model that's designed to be secure and private. Scalable Bayesian rule list is a type of model that will give you the rules that it uses printed out in order of importance. And I think that's another really cool kind of interpretability. So you're not just stuck with linear models and decision trees these days. You have lots of options, and I encourage you to try them. OK, so much like regular good old-fashioned EDA applies, regular good old-fashioned model assessment applies, right? So what's your AUC curve in your training data? What's your AUC curve in your validation data? What's your AUC curve in your out-of-time test data? These different metrics that people use just to get a sense of how accurate the model is still important. Those metrics are still important. And this is a practice that's as old as machine learning and just something that we need to continue to do. All right, explanation. This is my favorite part. And if you're interested, please come up and get a book. We have a little booklet about this stuff. So I can, in 2019 now, nearly any model I can make somewhat explainable. Now, I don't necessarily condone that. I think what's really powerful is the combination of these nonlinear but still interpretable models and the post-hoc explanatory techniques, okay? So I can have my monotonic GBM that I can tell my boss basically how it works, and then I can use something like Shapley explanations and say for any given prediction that the model makes, exactly how much each variable contributed to every single prediction, and it's exact. It's not an approximation, okay? So I would say over the past 3 years, there's been an incredible amount of research and advancements in this space of explaining even very complex models. And I want to reiterate, I think you'll get the best results if you start with kind of a constrained or interpretable model and apply the explanations. But if you just want to apply the explanations and you've never tried that, you should. There's a lot of different explanatory techniques, okay? There's some links at the end of the slide, and I have a GitHub repo where I keep track of them, and it's just getting bigger and bigger and bigger. So there's a lot of techniques. One that we think is very promising is called Shapley values. And I'll spend a little time here because I think it's fundamentally important to this whole idea. So Shapley values are actually a technique that came from the 1950s. It took us until 2017 to bring it into machine learning. And the idea of a Shapley value originally was that it is a player's contribution to what's called a coalitional game, or a game where people can cooperate. And the way this gets mapped into machine learning is we don't think about people in a game, we think about features in a model. And so in a complex machine learning model, one of the things that sets them apart from linear models is we allow the features to have high degree interactions implicitly in most machine learning models. So the features are allowed to cooperate, essentially, like players in a game might cooperate. And what Shapley values do is they disaggregate the contribution of each variable for every single prediction, much like each person to the outcome of a game, okay? So that's the fundamental idea of Shapley values. And as you can see from the slide, people have been aware of them in statistics and machine learning for, say, 20 years. They're just very time-consuming to calculate. Because basically what Shapley says is, I am going to take a variable out of the model and see what the prediction is. And then I'm going to compare that to the prediction with the model. Well, I'm sorry, I'm going to compare that to the prediction of the model with the variable. And so I'm not just going to do that once, though. I'm going to do that for every single row. I'm going to do it for every single subset of variables that includes the variable that I'm interested in. And then I'm going to take a weighted average of all those different predictions, and that's going to be the contribution of this one variable that I'm interested in. And that's a very expensive calculation. Naively, it's an exponential time calculation. So in 2017, a really brilliant guy at the University of Washington figured out a way to take Shapley values from being an exponential time complexity calculation to a log polynomial time calculation. And that's a huge deal, because that means it will actually finish in a reasonable amount of time most of the time. If you have a ton of variables, it's still really slow. So these are very, very accurate and what's called consistent variable importance measurements, okay? And that means that if I change my model a little bit or I change my data a little bit, I won't see my ranking of variable importance just totally get reshuffled. So one other thing that I like to add here, people always ask is, can I use this in credit scoring? And the answer is, I don't know. You'll have to fight with your own regulator about that. But Lloyd Shapley did win the Nobel Prize for this in 2012. So it's a relatively accepted and well-known technique, which I think is one thing that regulators look for. So, again, I want to emphasize there are just many, many different kinds of explanation techniques. And what Shapley is it tells you the feature contribution for every single row in your data set, and it does so very, very accurately. There's probably hundreds of other ways to explain machine learning models, and you should check them out. I just like to draw people's attention to Shapley values. Other common things are things like partial dependence plots, or ALE plots, or ICE plots. Lime is very popular. It just depends on the domain in which you're working. And if you are not working under incredible regulatory scrutiny, you might not have to do Shapley values. You might be able to get away with less computationally expensive explanations, or explanations that you like or made up on your own. I just talked to a company that had done a really good job making up a completely new kind of explanation that I'd never even heard of. So there's lots going on in this field, and it's very interesting, and you should dive in if you haven't. OK, so model debugging. Model debugging is a really new term. It's definitely related to model diagnostics. The first academic workshop about model debugging that I'm aware of is going to happen in about 2 weeks at ICLR. If you're interested, you should go. Model debugging, the way I would define it is testing your model to try to find problems, say, with accuracy or security that you can fix. So the libraries that I've highlighted on the slide are different types of tools that might help us find problems with our models. But they're all based on a very fundamental idea, and a very fundamental idea in model debugging is something that I would call sensitivity analysis, and something that if you're doing machine learning, you should probably be doing this. So if I have a linear model and the highest income my model sees in training is $500,000, I know exactly what my model is going to predict if it sees an income of $1 million. But if I've used a really cool 90-layer deep learning neural network, or I've used my XGBoost or CatBoost or whatever new gradient boosting algorithm there is, if I've used one of those libraries, I actually have no idea what my model is going to predict if it sees $1 million in new data. So the only way to know that is to test it explicitly. And a lot of model debugging is about just setting up tests for your models. And so Clever Hans is a library that's meant to find adversarial examples. And an adversarial example is a row of data that will make your model switch its predictions. Okay? And so we can learn a lot from adversarial examples because I can see which variables are really important for this person. Right? If I can flip this person's prediction, then I know that change that I've made to the data is really important, and that variable is really important for that person. It's also important from a security perspective. If there's one variable that I can change dependably to get the outcome of the model I want, then that model is very easily hackable. And I think hacking of machine learning models, while definitely possible, is a somewhat exotic concern. But if you have a prediction API sitting out right now, and especially like if you're loaning money to people or something like that, you need to be aware that like I know how, people know how to steal your model. And so you would want to do model debugging to know if there was a certain variable, like if I could steal your model, if I could get a copy of your model, which I know how to do, then I could do sensitivity analysis on it, and I could understand which variables I could use to switch the predictions. Okay, so if I could then I can then get the predictions I want out of your model, right? And so I can get your model to loan me or someone I like lots of money. So the adversarial examples are important from an accuracy perspective and a security perspective. PDP box is just a nice open source tool for doing partial dependence, but it also tells you how much data you have in certain areas, right? And that's a really important model debugging concept. If your data is very sparse for certain values of certain variables, your model's not going to do, it's just going to be luck if your model makes good predictions there. And so PDP box has a little tool for helping you find that, and I think that's often a concern that people forget about. What if tool is exactly like what it says. So what if tool is a tool that Google made. It's on the TensorFlow GitHub that just allows you to play with the values of your variables and see what happens. And I think that is a very powerful debugging, explanation, fairness tool, right? If I see that I can switch someone's gender and get a huge swing in the predictions, that's really bad from a fairness perspective in most cases, right? If you're dealing with medical data or something, maybe you want that, but in most cases you would not want that. So it helps me, if I can just change my data and see what happens, that's a very impactful testing tool. And if you're using nonlinear models, especially just getting started in nonlinear models, you need to do this kind of testing. Because I assure you, your model could do things that you don't expect outside the domain of your training data, and you will not know unless you test it explicitly. So we can move on to fairness. And these are some good open source tools. And again, I don't even like to use the word fairness. I believe in fairness, but no one can agree on what that means. So I like to talk about disparate impact, because that's been legally defined for decades. And I said it once, but I'll say it again. So disparate impact is when your model, and the rule of thumb is 4/5, okay? So the rule, it's called the 4/5 rule. So disparate impact is when your model makes predictions on a certain group of people that are more than 20% different than from another group of people, okay? And it's a very complicated question as to whether that's right or wrong. That's just the legal definition of things for people that are doing lending money, big banks that are lending money that have to comply with fair lending regulations. They are basically not allowed to have their model make 20% different predictions for one group versus another group. And those groups can be variously defined. They can be ethnic groups, they can be gender groups, they can be age groups. So you have to test it across a lot of different kinds of models. But the basic test is very simple. And I think if you're doing machine learning that has anything to do with people, you probably owe it to yourself and your company to do this, okay? Because you don't want to get dragged on Twitter. You don't want to get an article. You don't want to be the next person in the New York Times that has an article about how their AI system is biased, okay? And the basic test here is just to look at things like the false positive rate or the true positive rate and say, is that 20% different for men than it is for women? And I bet that most of the people in this room can figure out how to do that right now, sitting in the chair in their heads, okay? It's the basic test is very simple, and if you're doing machine learning that affects people, then, this might be very interesting to you, and I would urge you to do it. The last time I gave this talk, a guy came up and said something funny. He said, well, I just try to predict when washing machines break, so do you think I need to do this? And I was like, probably not. But if you're doing something with people, you probably should do this. Now, there's much more advanced variants of this, and you can get really deep into this, much like you can with explanations. And so, another best practice here is to pick the model with the least disparate impact, okay? And this is a big change from linear modeling. Because when you do linear modeling, you typically only have, let's say 5 to 10 models to choose from, right? You have 5 to 10 different accurate linear models that you can set up in one data set. And then you would pick the one that has the least disparate impact. And you might pay, a somewhat significant accuracy penalty for that, but if you're doing fair lending, you have to. I have a friend who's a compliance consultant, and he's done all these simulations, and he says that you can usually find a nonlinear model that has almost no disparate impact that has the same accuracy as a nonlinear model that does have disparate impact. So there's this thing in machine learning called the multiplicity of good models. And what that means is for any given data set, there's just a lot, like maybe infinity, good models. And so you can usually find one that has less disparate impact significantly than others. So then, if you look in some of these open source toolkits, which are really interesting, you'll see even more advanced techniques. And they basically break down into, like we talked about earlier, pre-processing the data to remove causes of disparate impact, regularizing the model, so putting a penalty on the model when it emphasizes people's personal characteristics too much, or post-processing your decisions so that they have less disparate impact. So the standard practice is called disparate impact analysis, and you select the model with the least disparate impact. The more advanced techniques try to pre-process causes of disparate impact out of your data, try to regularize it out of your model, or try to post-process it out of your decisions, roughly, if you bend them into just 3 buckets. OK. This one's really crucial. And again, if you don't care about anything that I'm saying from a, if you're like, this guy's crazy, I just need to build the most accurate possible model, great. You should still do this, OK? Because this is a way to preserve knowledge. Like when all your hotshot data scientists go get a job at a different company, you'll have a report that shows what they did. And I think that's just a very basic, good business practice, OK? And Google actually wrote a paper about this recently called Model Cards for Model Reporting, but it's something banks have been doing for decades. There's lots of good things here. And basically, you want very basic information in the report. What day was the model trained? Who trained it? Who do I call if there's a problem? That's a big one. If this model starts giving really haywire predictions in the middle of the night and costing me a lot of money, who do I call? That would be a great thing to have in your model report. We actually, every model that we train and using H2O driverless AI, we generate a very basic report that has things in it like just the name of the data set, what user was logged in, what features were originally in the data set, what features were engineered, what kind of model was it. You want just basic IT information about what's in your model, who trained it, when they trained it, and what to do if something goes wrong. Okay? And again, it's just a sound business practice, if nothing else. Deployment. Probably at this conference, deployment isn't such a foreign concept to most people. But I think a lot of data scientists, at least when they're getting started, really struggle with this idea of, I've got all my beautiful Python code on my laptop that's perfect and beautiful, and now you're telling me I have to put it on some server and it has to be converted to C#. But that's the way things work in the real world. And so your model, and I teach, and the way I always emphasize this to my students is, everything we've talked about so far just costs your company money. Okay? You're just a cost center until you get the model deployed, and then that's when you see if it actually makes or saves money. Okay? So again, deployment is a very important aspect of this, and you need to be aware of it from the beginning. And the way this ties in is the undue complexity piece. If you have a lot of unnecessary complexity in your model, it's just going to be hard to deploy for no reason. So it's going to take time to deploy. And that time that it takes to deploy will cost you accuracy, because the actual situation, the new data in which your model will be scoring, will have drifted away from the data that was there on your laptop with all your beautiful, perfect Python code. Okay? So just keep that in mind. Human appeal. Think about this very often, but it's super, super important. If you are doing machine learning that involves making decisions about people, like I said, I'm not a fairness expert, I'm not an ethics expert, but this seems very, very clear to me. If you are making decisions about people, they should be allowed to appeal those decisions, because we all know there can be all kinds of data quality problems. The model can just be wrong. The data can just be wrong. We don't like to think about that, but that's very often a possibility. So the example I give here, I live in Washington, D.C., and I have a young baby. And so I'm constantly trying to find nannies and babysitters. And there's all these apps now that rank babysitters. And if one of these apps says you're a bad babysitter, DC is an expensive place to live, much like the Bay Area. And these are people that make $20 an hour or something if they're lucky. And all of a sudden, your paycheck to paycheck job just got taken away by some kids in San Francisco or wherever the app was made, or DC, whatever. It doesn't matter. So that's a horribly unethical thing to do, and I would not condone doing that. So if you are making decisions, if your machine learning application is making decisions about people, you owe them the ability to appeal it. I just think from an ethical standpoint, and all the credit reporting regulation is based on this concept, right? If you've ever been denied a credit card, they're supposed to tell you what you could do, what you can change to get the credit card. And so again, like I was saying, a lot of this stuff just comes from best practices in financial services. All right, iterate. We all know that data science is an iterative process. Just think about things besides accuracy, right? Because I'd argue that your test data accuracy isn't as meaningful as we all hope it is, right? So think about privacy, think about interpretability, think about security, think about fairness. And if you can improve on one of those attributes, maybe it's okay to give up a little accuracy in a static test data set. All right. We're all into automation now. Certainly H2O is into automation. How much of this process can be automated? I don't know. And what is ethically appropriate to be automated? Can it all be automated? Maybe. I don't know. That iterative loop, can that be somehow done by reinforcement learning, right? Because we're talking about putting people in the process, but one reason we're trying to take people out of the process is because people have their own biases too, right? And so there's this balance between, can I automate parts of this to take people's bias out? Or should I put people's biases more in? It's a hard question. And I think apps could be a really good way to handle the human appeal, right? I got this decision about me. I think it's wrong. I press a button on an app. That seems reasonable. But you guys might have better ideas. All right. I focus on the interpretability and explainability aspects of this. And if you are working in fintechs or credit scoring, I think you'd find the top link extremely helpful if you haven't seen it before. The bottom link is the link I was talking about that just has like tons and tons of fairness, explainability, interpretable models, links. So, if you're interested in that, please check it out. And I think that's it. Maybe we have time. Looks like we have time for one or two questions. The rest, assuming you guys can get these slides, I tried to be really careful about the references. So if you want to go look at some of those papers that I was referring to on the slides, they should be there. But we can do a question or two. OK, I just saw you first. You have to go to the microphone, is what I was told, that you have to.
Just out of curiosity, is there like a bias that you felt for yourself? You don't have to say which one it was, and how did you realize that there was bias, and how were you able to debug it?
So I think the question is, have I injected bias into my own modeling processes, and did I ever catch that myself? I'm sure I have. I'm 100% sure I have. I can't think of an example off the top of my head, but I'm 100% sure I have. And again, the way to catch these things is with what's called disparate impact analysis. It's easy. The basics of it are easy. You can do it. So I'll try to think of an example for you.
So thank you for the presentation. So we talk about explainable modeling, right? Mm-hmm. So what kind of technology you use to explain model in
well, I'm obviously, OK, so that top link will show you exactly what I would do, OK? So, but I'll just say it right here. If I didn't work in some Silicon Valley machine learning company and actually had to really train models for a living, right? I just make the tools for them. I would do monotonic XGBoost with partial dependence and ice plots. And I would do Shapley explanations for my global and local feature importance. And if you go to that link, that's the first Python notebook you'll see. So I love monotonic GBM with Shapley explanations and partial dependence and ice plots.
Thank you.
You're welcome. Go to the mic. Sorry.
So I think I got a little confused. You talked about not using autoencoders as features because they're not explainable. But are you saying that you need to use these specific models if you want interpretability? You also mentioned once that you can explain any model. So let's say
sure.
You have a...
That's right. Very good question. So she said I said something kind of contradictory, which was you can kind of explain any model, but then I'm telling you don't use autoencoder features. And so to give a little clarification on that, you can explain autoencoders. It's just going to be harder. It's just going to be a lot harder, right? And so if you have these complex features in your model and explanation is important to the project that you're working on, you're going to have to spend more time, like perhaps way more time than it took to actually train the model and get that set up to explain those autoencoder features. But there's lots of techniques like integrated gradients, layer-wise relevance propagation. There's lots of techniques for explaining neural networks. So Good question. Thank you for the clarification. All right, we can do one more quick one. All right, I'll be around I can hang out there. I'll be at the H2O booth. Thank you guys so much for your attention today. Oh, and come get a book if you want.